Okay. So let's start with a review of what we did last time, and then I will take questions if anyone has any. All right, so last time we continued our discussion on propositions and compound propositions. We talked about conditional statements a little more. Statements of the form if P then Q. We talked about when they're true and when they're false. We also discussed their converse, inverse, and contrapositive. Okay, we talked about logical equivalence. Right, we said two compound propositions are logically equivalent if they always have the same truth values. We also said a conditional statement and its contrapositive are logically equivalent to each other. Okay. We discussed biconditional statements. Those are statements of the form P if and only if Q. Okay, that's a statement that's saying that P implies Q and Q implies P. Okay. Biconditional statements, we said, are true whenever P and Q have the same truth value. So if they're both true or if they're both false, then the biconditional statement will be true. Okay. All right. So any questions on any of that? We also discussed last time translating English sentences into logic expressions. And vice versa, and the opposite as well. Okay. Okay, so any questions on anything from last time? All right. So any questions from the homework problems? Okay, I'm not collecting the homework problems, but I will go over any questions that you had. All right, we have a couple of requests here. Let's see, let's start with 9H. Give me one moment to look it up. Okay, so let's start with 9H here. In question 9, this is in section 1.1. Okay. You were told the following. P and Q are the propositions. Swimming at the New Jersey shore is allowed, and sharks have been spotted near the shore, respectively. So P is the statement, swimming at the New Jersey shore is allowed. Q is the proposition, sharks have been spotted near the shore. Okay. So you're asked to express each of these compound propositions as an English sentence. You are given the compound proposition not P and P or not Q. So let's translate this. Not P would be the sentence, swimming at the New Jersey shore is not allowed. Okay, so swimming at the New Jersey shore is not allowed. Then we have a conjunction, so that's the word and. Okay. Okay. Actually, I'm sorry. Grammatically, the comma should be before the and. Okay. Swimming at the New Jersey shore is not allowed, comma, and now we have a disjunction here inside the parentheses, P or not Q. So I'm going to write that as either P, either swimming at the New Jersey shore is allowed, or sharks have not been spotted near the shore.
Professor?
Yes.
Wait, is that question 9 or question 11?
In my book, it's 9.
Oh, okay. Thanks.
No problem. Okay. All right. So notice we had this expression here, the disjunction in parentheses. Okay. So to sort of imply that there are parentheses here, I sort of stuck in the word either into the sentence. Okay. It helps to break up the sentence into 2 parts. Do you need the word either in there? Not necessarily, no. It just sort of helps us to make the sentence a little bit clearer. Okay. Yeah, if you have a different edition, then I'm using the 7th edition. So if you have a different edition, the problems might be off a little bit. Okay. 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 So that was that problem. Let's see. Next was 35F. Let me take a look at that. So for 35, you were asked to construct a truth table for each of these compound propositions. All right, and you're given the proposition not P if and only if not Q, if and only if P if and only if Q. Okay, so you got 3 biconditional statements here. Okay, so to construct a truth table for this, I start with the variables P and Q. I have a not P and a not Q, so I do that next. Okay. I have a not P if and only if not Q. I have P if and only if Q. And then I have my entire statement. Not P if and only if not Q. If and only if P if and only if Q. Okay. All right. Let's plug in everything. We start the same way as always. True, true, false, false. True, false, true, false. False, false, true, true. For not Q, it will be false, true, false, true. All right, not P if and only if not Q. So biconditionals are only true when both parts, both sides have the same truth value. So on one side, I've got a not P. On the other side, I've got a not Q. So I look at not P and not Q, these 2 columns here, okay? In the first row, they both have the same truth value. They're both false, so the statement will be true. Next row, not P is false, not Q is true. Those are different truth values, false. Next row, again, different truth values, false. Last one, the same truth value, true. Okay, let's move on to the next one. I have P if only if Q, so now I'm looking at P and Q. Okay. Again, it's true. Biconditional is true when both sides are true. Both sides have the same truth value. So first row, true, 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 false. Different truth values, false. Different truth values, false. False, false, true. Okay. Final column here. So now my two sides are not P if and only if not Q, and P if and only if Q. So that's this column here and this column here. Okay. So again, whenever the truth values are the same, the biconditional will be true. First row, true, true, true. Second row, false, false, they're the same. It's a true statement. False, false, true, 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 true. Okay, so this biconditional statement is always true. Sometime, whenever you have a compound proposition that's always true, that's something called a tautology. We'll get to that a little bit later today. Okay. Any questions on this problem? Okay, the next question was 47. 47 was a question about fuzzy logic. You needed to read the paragraph before. Okay. Give me one moment here. Does the order matter? Oh, no, on a biconditional statement, the order doesn't matter, okay? In a biconditional statement, P if and only if Q is the same thing as saying Q if and only if P. Okay, only biconditional, because biconditional, there's a hypothesis and there's a conclusion. Okay, so if you change their order, then that's a different sentence. Okay. Okay, so for question 47, let's read the paragraph about fuzzy logic together first before we go over the question. So you're told, fuzzy logic is used in artificial intelligence. In fuzzy logic, a proposition has a truth value that is a number between 0 and 1, inclusive. So if the proposition is true, you give it a truth value of 1. 1 means true. If it's false, the truth value is 0. Truth values that are between 0 and 1 indicate varying degrees of truth, right? Sometimes things are mostly true, mostly false, okay? For instance, the truth value 0.8 can be assigned to the statement Fred is happy because Fred is happy most of the time, right? It's mostly true, most of the time he's happy, so we'll give him a 0.8, okay? And the truth value of 0.4 can be assigned to the statement John is happy because John is happy slightly less than half the time. Use these truth values to solve exercises 45 through 47. Yep, this is 47, yeah, thank you. Yeah, sometimes that happens in different editions. If you have a different edition and you want to check all the homework problems with me to make sure they're the same, you can do that. You can email me, or you could check with another student who has the 7th edition, okay? All right, so what does question 47 say? The truth value of the disjunction of two propositions in fuzzy logic is the maximum of the truth values of the two propositions, okay? So if you have a disjunction of two propositions in fuzzy logic, then the truth value will be the maximum of the two truth values. What are the truth values of the statements Fred is happy or John is happy, and Fred is not happy or John is not happy, okay? So we have the statement. Let's say P is the statement Fred is happy. Okay, and Q is the statement John is happy. Okay, the truth value for P, we were told in the beginning, is 0.8. For Q, it's 0.4. So the truth value for P or Q, we're told, is the maximum of the two. So the truth value is going to be 0.8. All right. You were also told in a previous problem that in 45, in the 7th edition here, that the truth value of the negation of a proposition in fuzzy logic is 1 minus the truth value of the proposition. Okay, so Fred is not happy, right? Not P. The truth value for that would be 1 minus 0.8, which is 0.2. And for not Q, that would be 1 minus 0.4, which is 0.6. Right? So not P or not Q, that's the statement. Fred is not happy or John is not happy. Okay. The truth value for that one would be the maximum of the two. This time its truth value would be 0.6. Okay. So that's 47. Right? Oh, that's fantastic. Somebody has uploaded a link to the 7th edition, to a PDF copy of the 7th edition. It's in the chat here if anyone wants to make use of it. Thank you very much. Okay. Okay, so that was 47. Like the paragraph said, fuzzy logic is used a lot in artificial intelligence. A lot of machines nowadays sort of use fuzzy logic to some degree. Okay. All right, let's go on to the next problem. All right, somebody asked about, somebody asked about 15E. Okay, give me one moment to look that up. Okay. All right, so question 15 was as follows. Let P, Q, and R be the following propositions. P is the proposition grizzly bears have been seen in the area. Q is the proposition hiking is safe on the trail. R is the proposition berries are ripe along the trail. Okay. So we're asked to write the following propositions using P, Q, and R and logical connectives, including negations. Okay, and you're given the sentence, for hiking on the trail to be safe, it is necessary but not sufficient that berries not be ripe along the trail. And for grizzly bears, not to have been seen in the area. Okay. Yes.
Professor,
Yes.
necessary but not sufficient is a conditional statement.
So
in other
there's two sentences going on here. All right. There's two parts. We can break this up into two parts. Part number one, the necessary part of the sentence, and the second part, the not sufficient. Okay. So we can break this up into two things. All right. And the but here tells us that this is a conjunction, right? But is the same thing as and. All right. So that's really what we're going to do here. I'm going to break this up into one sentence, which is saying the first thing is necessary for the second thing. And the second part, which will be, it is not the case that the first thing is sufficient for the second thing. Okay, remember, not is the same thing as saying it is not the case that. Okay. Any other questions before I continue with this one? So yes, there are going to be conditional statements here. To answer, the simple answer to your question is yes. Okay. 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 So this here, hiking on the trail to be safe, right? That is Q. Okay. Necessary tells me I'm going to have a conditional statement. Not sufficient is not sufficient is a conditional statement. Berries not be ripe along the trail. If berries are not ripe along the trail, that's the negation of R, so that's not R. Not R. Okay. And that's again a conjunction. And for grizzly bears not to have been seen in the area, that's the negation of P, so that's not P. Okay. Okay, so I've got Q is necessary, Q for hiking on the trail to be safe, Q is necessary for berries not to be ripe along the trail and for grizzly bears not to have been seen in the area. So I'm going to do the necessary part first, okay? Whenever I have a conditional statement with the word necessary, remember, whatever comes before the necessary is the hypothesis, right? I believe if I said that correctly, or did I say that backwards? Give me 1 second here. No, no, okay. Yeah, okay. The way I told it to you was as follows, okay. I gave it to you as follows. If you have a statement, a conditional statement, if P then Q, okay. I told you that this is the same thing as saying if P then Q, and that's the same thing as saying Q is necessary for P. Okay. For P, whatever comes after the word for here, that's your hypothesis. Okay. So in our sentence here, I'm just looking at the necessary. I'm going to ignore the but not sufficient for a moment. We'll come back to that in a second. I have necessary, so that tells me this is a conditional statement. I have the word for here. Okay. So whatever comes after the word for, that's going to be the hypothesis. Okay. So this is saying the same thing as Q, if Q, then not R and not P. Okay. Okay. That's the necessary part of the statement. Okay. All right. So for hiking on the trail to be safe, it is necessary that berries not be ripe along the trail and for grizzly bears not to have been seen in the area. Okay. All right. Let's move on to the next part. Okay. But not sufficient. But is the same thing as and. That's a conjunction. Okay. All right. Not sufficient. So not sufficient. It is not the case that it is sufficient. Okay. Now, the not is a negation there. Sufficient is again a conditional statement. Okay. The way we did sufficient was I told you if you have a sentence, if P then Q, that's the same thing as saying P is sufficient for Q. Okay. So this time, the 4Q, that is your conclusion, okay? And the other part is the hypothesis. So here, hiking on the trail to be safe will be the conclusion, okay? And the not R and not P will be the hypothesis. All right. So here we have, it is not the case that not R and not P implies Q. Okay. And that would be our answer for this one. Are these the same statement? A sufficient condition for Q is P, a necessary condition for P is Q? Yes. Yes, those are the same. They're saying the same thing. Okay. Okay. Any other questions on that example? Okay. All right, let's move on to the next requested problem here. Next was 17E, but I think maybe that you were asking for 15E. I think you had a different edition, right?
Yeah, it was different.
Okay, okay. Next was 23D and G. 23D and G. Give me a moment to look it up. Let me see. Okay. 23, write each of these statements in the form if P then Q in English. Okay. So for D, you were given the statement, it is necessary to walk 8 miles to get to the top of Long's Peak. It is necessary to walk 8 miles to get to the top of Long's Peak. Okay. So we want to write this in the if-then form. So we have to figure out which sentence is the hypothesis, which sentence is the conclusion, okay? So let me refer to these two sets propositions here as R and S. Let's say R will be the proposition, you walk 8 miles, or and let's say S is the proposition, you get to the top of Long's Peak. Okay. All right, you walk 8 miles, you get to the top of Long's Peak. Okay. So reading this sentence, you have to sort of figure out what the sentence is saying. It's saying when one thing is true, something else also has to be true, okay? That's what a conditional statement tells us. It tells us that when one thing is true, it forces something else to also be true, all right? This sentence is saying it's necessary to walk the 8 miles to get to the top of Long's Peak, okay? So in other words, it's telling us that if you have a person that got to Long's Peak, to the top of Long's Peak, he had to walk 8 miles, okay? So in other words, S here is the hypothesis. S here is the hypothesis, and R is the conclusion, okay? So this is the same thing as saying, if you got to the top of Long's Peak, then you walked 8 miles. Okay, it's not saying that if you walk 8 miles, then you will have gotten to the top of Long's Peak. Okay, it's saying a person who got to Long's Peak, the only way he could have gotten there is if he walked 8 miles. So if I tell you a person got to the top of Long's Peak, you know he must have walked 8 miles. Okay, all right. So walking 8 miles is necessary to get to the top of Long's Peak. All right. Yes, R imply, no, S implies R. This is the same saying S implies R, like that. Okay, which one, in other words, which one is forcing the other one to be true, right? Okay, and a conditional statement, if P, then Q. Yeah, so that would be a different sentence, right? That's not the sentence here that's being given to us. If you switch these two, right here, in this sentence, S here is the hypothesis, and R is the conclusion. If you switch the two, you get a different sentence, right? If I write down the opposite, if I write down the converse of this, right? The converse would be if R, then S. That would be the sentence, if you walk 8 miles, then you will get to the top of Long's Peak. Right? So this sentence is saying something very different from the previous sentence. Okay, this sentence is saying you take any person, wherever he is in the world, have him walk 8 miles. At the end of walking 8 miles, he'll be at the top of Long's Peak. That's what this sentence is saying. Okay, that's not what the first sentence I wrote down is saying. The first sentence I wrote down is saying, if you got to the top of Long's Peak, then the only way you could have gotten there was to have walked 8 miles. Okay, so they're two different sentences. Okay.
Professor, how do you know to identify which one is R and which one is S?
Good question. So again, you can sort of, as a shortcut, you can sort of use the list of common ways that I gave you. Or you can also try and ask yourself what the relationship is in the sentence. Which one is forcing the other to be true, right? So again, if you go back to this sentence here, it's necessary to walk 8 miles to get to the top of Long's Peak, right? Again, what is that saying? That's saying, if you got to Long's Peak, how did you get there? The only way to get there was to walk 8 miles. So if you got to the top of Long's Peak, then you had to walk 8 miles to get there, okay? All right, if you have a person that comes up to you and said, I got to the top of Long's Peak, then what do you know? You know, oh, he had to walk 8 miles. Okay, so that sentence, if I tell you I got to Long's Peak, that forces something else to be true. You know I must have walked 8 miles to get there. So if S, then R. If I got to the top of the peak, then I had to walk 8 miles. In a certain sense, yeah, in a certain sense, S is forcing R to be true, right? If I tell you S is true, you know R has to be true for the statement to be true. Right? If I tell you I walked 8 miles, that doesn't mean I got to the top of Long's Peak. But if I tell you I got to the top of Long's Peak, you know I had to walk 8 miles to get there.
Sir, I had a question.
Go ahead. So the same thing. So the same thing from before applies, as in whatever is stated right after necessary becomes the if statement.
Not necessarily. Again, it's sort of sometimes the structure of the sentence can be weird. This is the issue with language and with English also, right? The structure can be a little bit strange sometimes, all right? Which is sort of why we have the logic symbols to sort of give us a nice form for many different ways of saying a sentence. You just have to sort of read the sentence and try and see which one makes the other one, which one implies that the other one is true.
Sir, doesn't it depend on the initial condition? If the person is 8 miles from the peak, then we know that he had to. If he is at the peak, then he walked 8 miles. But if the initial condition is different, so how does that work? So if let's say he's not 8 miles, he's let's say 16 miles from there, and we know he got to the peak, but now we cannot conclude that he has to walk 8 miles, but because he actually walked 16 miles.
So that's sort of already out of the scope of what the sentence was telling us. Okay, here we were just sort of trying to rewrite the sentence. That's all we were trying to do. All right. Okay. So given this situation, here's a sentence. Without all the question asked you to do is rewrite it. That was all. Okay. In a situation like you were trying to give me, let's say, like we were trying to give me, in that case, it might just be a false statement. In that case, all right. Okay. All right. Any other questions? All right. I think we had some more questions from the book, but time is running a little short. So I'm going to end the homework problems here. If you had some more problems you want to go over, we'll go over them again next time. And let's do some new stuff for the rest of class. Okay. All right. Okay, so we are now in section 1.3 in your textbook, which deals with propositional equivalences. Okay, all right, so this section deals a little bit more with logical equivalence. We're going to start with a couple of definitions. Okay. First definition is for a tautology. Okay. So a compound proposition that is always true no matter what the truth values are no matter what the truth values are of the propositional variables that occur in it is called a tautology. Okay. So in other words, a compound proposition that is always true is called a tautology. Okay, you have a proposition, you have a statement that's always true, that's a tautology. Okay. Okay. A compound proposition that is always false is called a contradiction. Okay. If you have a compound proposition that's neither a tautology nor a contradiction, meaning it's sometimes true, sometimes false, which is most of the compound propositions we've seen until now, that's called a contingency. Okay, so a compound proposition that is neither a tautology nor a contradiction is called a contingency. All right, so again, a contingency is just a compound proposition that is sometimes true, sometimes false, right? It can be either true or false. Okay, so for example, we already saw one example of a tautology earlier today. From one of the homework problems, we had the example of not P if and only if not Q, if and only if P if and only if Q. Okay, that was an example of a tautology because it was always true. Okay, if we want to check if a compound proposition is a tautology, a contradiction, or a contingency, we can just check the truth table. Okay, as we saw in that example. Another example of a tautology would be the compound proposition P or not P. Right? That proposition is always true. We can check. Okay, let's write a truth table. So we can check to see if it's a contradiction, tautology, or contingency by using a truth table. So let's check this one here. All right, I have P, I have not P, and then I have P or not P. Okay, so I really have two possibilities. P is either true or false. Not P is either false or true, right? Not P has the opposite truth values of P. Okay, so either P is true, not P is false. P is false, not P is true. Disjunction, the disjunction will be true when at least one is true. So in the first row, P is true, it's true. In the second row, not P is true, so it's true. Okay, so P or not P will always be true. So it's a tautology. Okay. P and not P would be a contradiction, and we can check that again using the truth tables. So again, P, not P, P and not P, true, false, false, true. A conjunction is true only when both of its parts are true. True, false, 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 true, false. Okay, so the conjunction here is always false. It's a contradiction. P and not P is a contradiction. Yeah, sure. Yeah. Let me scroll up. Okay. Is that good, or you want me to go a little higher? Okay, good. Okay. All right, and then contingencies, we've seen plenty of contingencies already. For example, take the conditional statement, if P then Q, that's a contingency because it could either be true or false, depending on the truth values of P or Q, P and Q. Right, that's a contingency. Okay. All right. Any questions on that? Okay. All right. All right. So I'm now going to give you an alternative definition for logical equivalence. Remember, we said previously that compound propositions that have the same truth values in all possible cases are called logically equivalent. Okay. So this is an alternative definition for logical equivalence. Okay, so the compound propositions P and Q are called logically equivalent if the biconditional statement P if and only if Q is a tautology. Okay, and as always, we use the triple equal sign to denote logical equivalence. Okay, any questions so far? Okay. All right, I'm now going to give you a table of some important logical equivalences of statements that are logically equivalent to each other. For this table, so for the following table, okay, if I write a capital T, here in this table, for this table, a capital T denotes a proposition, and specifically it denotes a compound proposition that is a tautology. Okay, for the following table, T denotes a compound proposition that is a tautology. That's always true. And capital F denotes a compound proposition that is always false, or in other words, that is a contradiction. Okay, so here's our table of logical equivalences. Okay, some of them will be more important than others. I will point them out at the end. Okay. All right. So the first pair of logical equivalences are called the identity laws. Okay. There's two of them. First of all, P and T. So the conjunction of any proposition P with a tautology will be logically equivalent to P. Okay, so P and T will be true whenever P is true, and vice versa. Okay, and P and T will be false whenever P is false, and vice versa. All right, the second identity law, the disjunction P or F is logically equivalent to P. All right. The second logical equivalence, or pair of logical equivalences, is called the domination laws. Okay, so the two laws are as follows. P or T, the disjunction P or T, is logically equivalent to T, and the conjunction P and F is logically equivalent to F. Okay? And as a side note, all of the logical equivalences I'm giving you now in this table, you can prove that they're all true using truth tables, right? As we did, like we did last time. Okay. All right, number 3, the idempotent laws. Okay, so P or P, the disjunction of P with itself is equivalent to P, right? For the gamers, that's player versus player. And the conjunction P and P is logically equivalent to P as well. Okay. Number 4 is called the double negation law. Okay. So the negation of P, not P, is, as you would probably assume, is equivalent to P. Number 5, okay, the commutative laws. Okay. So this just states that conjunctions and disjunctions are commutative, meaning the order doesn't matter. So P or Q is equivalent to Q or P. Right? And same thing for conjunction. P and Q is equivalent to Q and P. Okay. So for conjunctions and disjunctions, the order does not matter. All right. As long as I have only conjunctions or only disjunctions. Number 6, the associative laws. Okay. So the associative laws basically tell us that we can move around parentheses. So if I have P or Q in parentheses or R, that's equivalent to P or in parentheses Q or R. Okay, and that's true as long as I have only disjunctions. Okay, and same thing for conjunctions. If I have P and Q in parentheses and R, that's the same thing as P and Q and R. Okay, and again, that's true as long as I have only conjunctions. If I have conjunctions and disjunctions mixed, then I'm going to need the next law, which is, well, can anyone guess what's next after commutative and associative? What do you think would be next? Yep, distributive. Exactly. So the distributive laws are for when, oh, somebody wanted me to scroll up. There. The distributive laws are for when we have conjunctions and disjunctions mixed. Okay. Okay, so that's next. That's going to be number 7. All right, so if I have P or, and then in parentheses, Q and R, that's equivalent to, so the P or, the P with the disjunction will distribute. So this is P or Q and P or R. Okay, and same thing for conjunction. So if I have P and Q or R, so I switch the conjunction and the disjunction, it's the same thing, I just distribute the P and. So this becomes P and Q or P and R. Okay. Those are the distributive laws. Next are De Morgan's laws. All right, De Morgan's laws are important ones. Okay, so De Morgan's laws you should know for the future. There are 2 of them. Number 1, let's say I have a negation of a conjunction, the negation of P and Q. Okay, it is not the case that P and Q. That's the same thing. That's equivalent to saying not P or not Q. Okay, so in other words, I can distribute the negation over a conjunction. I just have to change the conjunction, the and, into an or. Okay, and same thing for disjunctions. So the negation of a disjunction, not P or Q, is equivalent to not P and not Q. Again, so I can distribute the negation, but I have to change the or to an and. Okay. Okay. Next, number 9. Number 9, these are called the absorption laws. So if I have P or P and Q, all right, so notice I have a P repeating here, that's equivalent to P. And if I have P and P or Q, that's also equivalent to P. And finally, number 10, the negation laws. Well, I said finally, but I have a few more actually after this. The negation laws are as follows. P or not P is equivalent to T, that's a tautology as we saw earlier before, and P and not P is a contradiction. Again, we saw that one before. Okay, so from this table here, so far the most important ones you need to know are De Morgan's laws. Okay, the others are good to know as well, but those are the most important ones. I'm also going to give you a few more. So do you need to memorize all of them? No. Just make sure you memorize the ones that I tell you are important. So De Morgan's laws, make sure you know those, and I'll give you a couple more that you should know. Okay. The others you don't have to memorize, but it's good to be familiar with. All right. Okay. The next couple of ones I'm going to give you are for conditional statements. Okay. So the next ones are for conditional statements. Okay, so I'll call this one number 11. Okay. So P implies Q is logically equivalent to not P or Q. Number 12. The negation of P implies Q is equivalent to P and not Q. Okay. So this one here is also important. We'll see that again when we do proofs in section 1.7. And let me also put a star by De Morgan's laws. Okay. All right, 13. P implies Q is logically equivalent to its contrapositive. Not Q implies not P. That one is also important. We'll see that again when we do proofs. All right. That's it for the conditional statement ones. And let me also give you a couple for biconditional statements. No, these don't have any names. Okay. Okay. So 14. P if and only if Q is logically equivalent to P implies Q and Q implies P. Okay, that's really what a biconditional statement means, right? The statement P if and only if Q means this, means if P then Q and if Q then P, right? Each one implies the other. That's really what the meaning of a biconditional statement is. So that one's also good to know, number 14. And one more. P if and only if Q is logically equivalent to not P if and only if not Q. Okay, and then I'll give you one last one. This is something we've discussed before. P if and only if Q is equivalent to Q if and only if P. Okay, right, the order doesn't really matter for biconditional statements. Okay, all right, that's it for this table. All right, again, only the ones I put a star next to De Morgan's laws, plus these three here, those are the important ones you should know going forward. Okay. All right. Now, all of these equivalences, all of these laws that I gave you on this table, they can all be proven to be logically equivalent using truth tables. All right. So, for example, let's prove number 12 here using a truth table. Okay, let's prove that the negation of if P then Q is equivalent to P and not Q. We're going to prove this using a truth table. Okay. So if I want to make a truth table, I have my two variables, P and Q. I've got a not Q here. Okay, there's no not P. I have P and not Q. Okay. I have if P then Q, and then I have its negation, not if P then Q. Okay, so notice I first did if P then Q, and then I did another column for the negation of that. Okay. All right, let's plug in everything. P and Q, I start the same way I always do. True, true, false, false, true, false, true, false. Not Q is the opposite of Q, false, true, true. P and not Q, that's going to be P and not Q. That's a conjunction. It's only true when P is true and not Q is true. Both parts, both sides have to be true. Here's P, here's not Q. True, false, false, true, 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 false, 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 true, false. If P then Q, that's a conditional statement that's only true when P is true, but Q is false. So that's going to be true, false, true, true. We already know the truth table for that. Okay, now we have the negation of if P then Q. So here, this column is if P then Q. This one is its negation. Okay, so it will have the opposite truth values of if P then Q. So in the first row, if P then Q is true, so its negated statement will be false, opposite truth value. The next one is false, so for the negated statement, it will be true, and then false, and then false. Okay, let's look at our two columns now. P and not Q. The negation of P implies Q. Okay. If you look at these two columns, in each row, in each case, all the truth values are the same, right? They're both, in the first one, they're both false. In the second, they're both true. And then in the last two, they're both false. So because the truth values are the same in each case, they are logically equivalent. Okay, any questions on that? Yes, sure. How far up do you want me to scroll? Is that good, or should I go a little bit more?
Sir, I had a question.
Yes, go ahead.
Third row, P given not Q is false, false. Oh, never mind. Sorry. Got it.
You see
Got
it?
it. Yeah,
Okay.
got it. Thanks.
No problem. Okay. Okay. Any questions on that? Okay. I want to give you now one more definition here, and with that, we'll finish for today. Okay. So I'm going to give you a definition for satisfiability. So definition. Okay. All right, so a compound proposition is satisfiable if there is an assignment of truth values to its variables that makes it true. Okay, so in other words, if I have some compound proposition and there is at least one case, there's at least one situation in which the statement can be true, it's possible for this statement to be true, then that compound proposition is satisfiable. If I have a compound proposition that can never be true, in other words, it's a contradiction, then it is unsatisfiable. Okay. All right.
And what if it's always true?
Then it's satisfied. Okay, so if there is at least one situation, one case where it's true, then it's satisfiable. So a tautology would something that's always true would be satisfiable. If it can never be true, in other words, it's a contradiction, then it's unsatisfiable. Okay, so if there is no such assignment of variables, right, that makes the proposition true, then it is unsatisfiable. All right. When we find a particular assignment of truth values that makes the proposition true, that particular assignment is called a solution. Okay, so an assignment of truth values that makes the compound proposition true is called a solution. All right, so let's deal with a basic example of something we've seen before. Is the compound proposition, if P then Q, a very basic conditional statement, is this satisfiable? The answer is yes, right? Because there is a circumstance where it is true. Okay. What's an example of a solution? So a solution would be an assignment of truth values to the propositional variables that makes it true. So one solution would be where P is true and Q is true, right? Because under those circumstances, the statement is true. So one solution would be when P is true and Q is true. Okay. There are actually three solutions, right? That's one solution. Another solution would be where P is false and Q is true. And a third solution would be where P is false and Q is false. All right. In computer science and a lot of different types of problems, the question is asked, you have a statement, and the question is asked, is this statement satisfiable? Meaning, is there some circumstance where this statement will be true? Okay. What would be an example of something that's not satisfiable? Well, if you had something that's a contradiction. So for example, we saw before P and not P was a contradiction. So that is unsatisfiable. Right? There's no way we could make that sentence true. Any questions on that? Okay, if there's no questions, we are done for today. I will have your next homework assignment up on Blackboard. Okay. I believe next week, I think if I'm correct, we do not have class on Monday. Is that correct for Labor Day? Yeah. So I'll see you guys next week on, thank you. I'll see you guys next week on Wednesday. I'll do the attendance now. Just let me know you were here. And after that, you can go. Take care, everybody. Have a good week. I will see you next week on Wednesday. Yes.
Professor? When is our first quiz going to
Good
be?
question. I'll either post something on Blackboard or we'll discuss it on Wednesday. Okay, I'll give you a heads up before.
Okay. All right.
Okay.
Have a
Take
good one.
care.
Professor,
Yes.
I don't remember if I put my name down last class. Would you be able to check if I was marked present?
Okay. Just let me know you're here today and that'll be good. You'll be fine.
I don't remember typing my name out.
All right. All right. No problem. No problem. Thank you. Okay. Any other questions? Okay. All right. I assume everybody by now has let me know they were here. I will stop recording now.